Hello all. So today's videos in this video we are just going to discuss about the universal gates and how we will be implementing all other basic gates using the universal gates. So we'll just start about the generally. So as we all know, so NAND and NOR gates are so. So as we all know, so NAND and NOR gate are called as universal gates. So why these things are called as universal gates means these are like we could implement all other basic gates logics using these two gates actually, NAND or NOR. So with any of them we could just we could implement the other basic gates, so that we are calling these as universal gates. So we'll just we'll see about all the examples here about the NAND and NOR gates. So just as a basic, we'll just start from the NOR gate. So here we will be talking about the NOR gate implementation using NAND gate. So that is what now we are going to see. So I'll just go by step. So first what we have to do is first thing what we have to do is here is that we have to write the truth table of both of that. Okay, so we know the functionality of the particular gate is we can just simply by seeing the truth table we can come to know the functionality of that. So as a first thing, so for the basic gates and its functionality and truth table, how to write the truth table, I have included in my previous videos. Please, I'll give the link for that also. Please look at that and you'll get to know about how to write the truth table. So here using the truth table, we'll just here we are just going to write the truth table. So the explanation you can see it in previous videos. So I'll just write the truth table of NAND gate and then NOR gate. So here what logic we are going to implement is NOT. So using what we are going to implement is the NAND. So first I will write about the NAND gate truth table. So we know the symbol also, these things you can get from there. So this is what the truth table will look like. We have a 4 set of inputs since we have 2 inputs, and here we all know it will be like this. So this is the truth table of NAND gate. Okay, so this is the truth table of NAND gate. So and all we know about the NOT gate. So NOT gate we will be having only one input, so the output will be the A bar. So for that then only one input we have, so we will be having 2 logics only. So this is what we have for NOT gate. So what we have to do, we are going to do now is, this is the input we will be getting from the external side, and this is the output we need to give to the external. So this is what the functionality we have to implement. So if we get the input as a 0 from the external, we need to give the output as 1 to the external. So if we get the output as input as 1 from the external, we have to give the output as 0. So this is what the functionality we have to implement. So for that what we are going to use, we have only the NAND gate available in the library. So we have only the NAND gate. So what we have to implement the NOT gate using the NAND. So we just have to compare the truth tables actually. So we know, right, initially this is C2 inputs, only one input it will be expecting, but we have 2 inputs at the NAND gate. So how we are going to handle those terminals actually. So what we have now, we have this only. We have this is the one we have currently, AB and ABD whole bar. This is what we have. Okay, so we'll just look at the truth table and come to know how we can convert this NAND gate to the we can have the number of NAND gates, but the primary intention is only using the NAND gates we have to build our NOT gates. There should not be any other gates involved, only NAND gate we should be having. So by seeing this you can get to know, right, anyway we will be having only one input from the external. So we should be connecting this directly to the input, to the both input we have to connect, or we have to connect this one to the same and this one with a separate one, or some constant value also we will be doing. So something like that we have to do to make this possible, right? So okay, so if you see here, you will just think about this one. Okay, here A and B are same, here B, A and B are same. You take this particular things. So from that what we are seeing, both inputs are 0 0, so that time we are getting output as 1. both inputs are 1, as this time we are getting output as 0. So if we do this particular NAND gate as both the inputs, if we make this as same, okay, so only one input we are getting, and this one also same, this one also same, that time if you see, the output will be the AB bar. So that is what we are getting. So if you see, it will be like both are same, definitely we are getting the output as high. Both are high, we are getting output as 0. So it will just implement the NOT gate functionality. So we are just shorting the inputs. So here, since A and B are equal, our thing will be A and A bar. A and A bar will be, we know, right? If A and A will be 0 0 means it will be 0, it will be 1:1 means it will be 1. So A and A will be A. So A bar is the operation here we are getting. Okay. So this is what about the one particular method to convert the NAND gate to the NOT gate. So in this, what we have done, just the NAND gate only one NAND gate. By shorting the inputs, we are getting the NOT gate. So this is how we will be implementing the NOT gate using the NAND gate. This is one of the method. And if you see, okay, here this functionality we just used, right? So both are equal means definitely the output will be the inverted version of that one, that we saw already. So now we'll look about some other scenarios. Okay, we have this type of things, right? So if you see this one, these things, yeah, okay, look at this. If any of the inputs, okay, here if you can see one another pattern, right? If you see, if the inputs are one of the input is high, the output is just an inverted version of the input. You could see from this here, you can see, right? So if the A is 1, the output will be the B bar. So what we can do, like this also can do the NOT gate implementation. So one input will always connect to VDD. VDD means that high will be connecting to that, and one of the input what we are giving, it will be the inverted version of that one. So this is one another technique of converting the NOT gate, of converting the NAND gate to the NOT gate. So just then implementation of NOT gate using our NAND gate. So this is what we could do. Okay. So from the truth table itself, here we just implemented, right? So we can compare the truth table of that. So from that we can just get a information that this is how the NOT gate can be implemented using the NAND gate. So yeah, this is the first basic implementation technique. Okay. So yeah, I think you all are clear with this. So yes, we'll just move to another one. Okay. So here, yeah, we'll just start with the AND gate. Okay. So AND using NAND. Okay. So this is what we are going to do now. So same what we have to do. We have, since it both have two inputs of things, we'll just write this one like this. AB is AND gate of that AND gate, and NAND is the AB bar. So just write about the truth table input combination. We all know how we have to write. So four set of inputs we will be have, 4 set of combinations we will be having for the 2 set of inputs, for the 2 inputs. So for this, you all know this will be this and this will be this. So basically we know, right? So the NAND gate is what? The AND gate followed by an inverter will be the NAND gate. Okay. So this is the AND we will be having. So inverter and this one we are having. Okay. And before seeing about this one, some another one thing also I will tell. We all know, right? First, if I give one input as consider I am giving as A. So the output of inverter will be the A bar. And if I again invert my output of the invert gate, what will be having? The output will be again A. So the 2 times, if a back-to-back inversion if I do, my output will resemble the input. So it will be the buffer condition. If both we have added the even number of inverters at our path. So if we have an even number of inverters in our path, it will be the buffer only. So this is one thing you remember. Okay. So two inverters we have added, so it will be just giving us the same input what we have given, but with the different directions and all. But that is a different concept. We can just go into depth after that sometime. Yeah, the back-to-back inverter also will be there in real design, so that we will talk about later. Yeah, but the back-to-back inverter will just give the, generally logically it will give the functionality of the buffer. Okay. So if we give input here A, the output also you will be getting A only. So this concept you remember. And here if you see, right, so we can see that AND gate followed by NOT gate only will be the NAND gate. So this is what we have currently. Okay, so this is what we have, AB bar we have. So from this what we can understand, one AND gate followed by NOT gate only this one. Again if I add the another one inverter at this path, I will be getting the output as AB, right? So as per this one, so if I have another inverter here, it will just these both will just logically this both will compensate the things, compensate the inversion property. So the output we will be having what we are having here only, we will be having here also. So this particular back-to-back inverters logically don't play any role here. So this is the the buffer role it's playing. So we will be getting the AB. So what we can do here also, we can add just an inverter to get our AB. Okay. So but what I told initially itself, so for this particular implementation techniques, we should be having the only NAND gates, we should not have any other gates. So for this NOT gate, as we already did, right, so we have this one, this particular concept or this particular thing, we have already implemented the NOT gate using the NAND gate. So we can just use any one of that. So currently what we will do, we will just use this one. Okay, we have to invert, right? So this like we will do. Now next AND gate will just short the input terminals and give only AB bar to that. It will give us AB. Okay, so here we are not at all using the truth table, the basic, but here what we are using, just we know the NAND gate is the inverted version of the NAND gate. So we just know that back-to-back inverter will play a role of buffer. So we have implemented our AND gate only with the buffer at the inverter at the output. So the inverter also we have implemented using the NAND gate. Okay, so this is what the implementation of AND using the NAND. Okay, yeah. Okay, so we have already how many basic gates we have? 3 gates, NOR, NOT, and OR. So already we have implemented the NOT and AND. So we'll go with OR now. Okay. So OR using NAND. Same. You just try to return the truth table of that. First, initially, you don't look at anything. Just you write the truth table of that. Okay. So 2 inputs we have, 4 combination of input we will be having. So we know OR operation will be like this, and NAND operation will be like this. So we return the truth table. Okay. So we have to implement this one. Okay, we have to implement this one. I will give this only. This is the inputs I will give, but I need to get output to this. But what logic I have is this. My current circuit, my current cell or circuit will just give me this one. Okay, this particular output, set of outputs, it is just giving, but I need to convert my input to this one. Okay, okay, only you look at now inputs are same. So same like AND again, now inputs are same. We no need to look at the input itself. We'll just see the outputs. What if from this what you could see, it is like 0 1 1 1, it is like 1 1 1 0. It's just a reversed form, right? If I just twist this particular output logic says up and down, it will be similar. So what I have to do, I have to make this I'll just make this 0 to come here, 1 to come here, 1 to come here, 1 to like this one. If I do, okay, this to this, this to this, this to this, and this to this. This is like I have to do. Okay. Output side, I can't. It's not like inversion, right? It is like it is not like the inversion at the output side. It is the inversion at the input side, because if you see, right, this is 1 1. If you see, the exactly invert version will be here, and next will be 1 0. Exactly the invert version will be here, 0 1, and the 0 1, next 1 0, this 0 0 1 1. So if you see, it will just if you just twist this one, it will be A bar B bar. Okay, we'll write once. Okay, A bar B bar also will write once. You will come to know exactly 1 1 1 0 0 1 0 0. Okay, if you see, right, if you just invert this one, this where it will come at the initial time. in 1 0 0 1 1 0. Now this for the 1 1, what we will be having 0 at the NAND gate only we have, right? So 0 1 1 1. Now this is what we are getting, the expected output of not OR gate we are getting through this one. How we have implemented this one? We just inverted the A and B. Okay, only the inputs we are inverting to get a OR gate outputs. So with this one we are not getting 0 0 means if I give 0 0 as an input to my NAND gate, it will give only 1. It won't give the 0. It will, if it is 0 0, it will give this one only, not give this one, something like that, right? So if I invert, so what it is expecting, if I give A bar and B bar here, I will be getting A plus B here. Okay, if I give A bar and B bar here, my output of NAND gate will be A plus B. That is what it is giving. From the truth table we can come to know. Okay, this it provided, and we know, right, how we have implemented the NOT gate using NAND gate. The simple as that, this like, okay, A bar, B bar, then we just give to one more NAND gate, that will result in A plus B. Okay.